Hi, I'm Sofia and I'm an engineer at Graphcore. Today I will guide you through GPT-J fine-tuning on a Paperspace notebook. In the notebook, we adopt the unifying approach presented in T5 paper for natural language processing task. The idea is that every task can be formulated as a text-to-text problem where the generative model is simply asked to generate the next token. Fine-tuning becomes very simple because you don't have to change the model architecture and you can simply train the model autoregressively to generate the next token. We apply this idea to fine-tune GPT-J on GLUE MNLI dataset. The task here is to determine entailment, which means that given a pair of sentences, an hypothesis and a premise, the model has to determine whether the premise entails the hypothesis contradicts the premise, or the two sentences are neutral to each other. In the notebook, you will learn how this task can be casted into the text-to-text format and how you can use our very simple API to fine-tune the model on IPUs. The code is very easily adaptable to other datasets and to your custom fine-tuning. Let's get started. From the Paperspace homepage, you need to log in and you need to create a new notebook. The correct runtime to select is PyTorch on IPU, and you need to select either an IPU pod 16 or above pod 16 because this is the minimum hardware requirement for the application. After that, you can start the notebook. Once the machine is running, you can navigate to the notebook. You should find a GPT-J text generation folder on the left, and you can open the fine-tuning notebook. This is the view you should have. We can also open a terminal. We will need it later. So terminals, add, and we have our terminal. The first cells are just to set up the environment. And you can notice that here we define the checkpoint directory. This will be the place where we are going to save the trained weights, and we will access this folder from the terminal. After setting up the environment, we can load a configuration for both fine-tuning and validation. Let's run all the relevant cells and go up. We also support logging to weight and biases, but an extra setup is needed for that. Follow the instruction on the notebook if you want to log your loss to weight and biases. You need to have an account, obviously. The configuration, as you can see, contains all parameters defining the model architecture, but also some parameters which are related to the execution on the IPU, and the training parameters to define the optimizer values and training step and so on. There is also a configuration for checkpoint, meaning where and when we want to save the model weights during training. Don't worry, we will guide you through all the relevant parameters later on when customizing the configuration. Once we have a configuration for both training and validation, we can move to dataset pre-processing. As we said at the beginning, MNLI dataset is a dataset for entailment, meaning that the task is to predict the relation between the premise and the hypothesis, which can be entailment, contradiction, or neutral. You can explore the MNLI dataset on Hugging Face dataset preview. We are interested in the train and validation mismatch dataset. As you can see, we have three relevant columns, one containing the premise, one containing the hypothesis, and one for the label, which is an index corresponding to the three different categories. For training, what we want to do in order to cast the dataset into a dataset which is suitable for text generation is we want to form training prompts where the model is simply asked to predict the next token. So what we do is we build this kind of prompts where we have an hypothesis tag, and then we put the hypothesis, a premise tag, and then we put the premise, and the label tag, and then we put the label. So after loading the dataset, we use this form training prompts function, which takes items in the original dataset and build this kind of prompts for training. It will take a while to download the dataset and apply this function. Once prompts are ready, we can show you the difference between the original items and the items after applying the form training prompts function. Okay, so you can see at the beginning we have the premise. This is just the first item. We have the premise, the hypothesis, and the label. And after applying this function, we just have a single text prompt containing our prompt. The next step is loading GPT-J tokenizer and tokenizing the prompts. Tokenization is the process of converting actual text to input IDs. Okay, so you can see that now we have indices instead of text. The next step is to apply, to pack together the sentences up to the model sequence length, which is 1024. And we don't need any special way of separating different sentences because the task is just to predict the next token. And all future tokens are automatically ignored because we have the causal mask. GPT-J is a causal decoder-only model. This function, group text, not only takes the different sentences and build groups of build sequences of 1024 tokens, but also separate input IDs from labels. If you think about it, if our task is to predict the next token, the label for a given sentence is the same sentence shifted by one. And here you can see the first 10 tokens of the first sentence. And you can see that this is the input IDs and this is the labels, and they are shifted. For validation, the pre-processing is very similar. The only difference is that we don't include the answer in the sentence. So let's run the pre-processing. And as before, you can see the difference between the initial dataset and the pre-processed one. Okay, with pre-processed datasets and a base configuration for training and a base configuration for validation, we are now going to customize the configuration. For training, the relevant parameters are the training steps, the dropout probability, all the parameters related to the ADAM optimizer, and parameters related to checkpoint. First of all, there is the checkpoint directory, which we are going to set to the previously defined one. And then we have to define how often we want to save the model and how many checkpoints we want to keep in memory. One other possibility is defining if we want to include the optimizer state in checkpoint or not. This is useful only if you want to resume your training at a later time. We recommend not to save checkpoints too often because this is a time-consuming operation. This load option is needed only if you want to resume training from a previous checkpoint. For validation, the relevant parameters are the output length, which is the maximum number of tokens generated by the model. This can be set to a small number because our target words are very short. It's just entailment, contradiction, neutral. And the output length can be combined with the maximum length of sentences encountered in the dataset to shrink the model sequence length to a smaller number with respect to training. So it won't be 1024, but a smaller number. This allows us to increase the batch size and perform validation in a more efficient way. Let's run all this cell. Okay, you can see that the maximum length is a lot lower. And this is the final validation configuration. And the last bit we need for validation is to load a metric needed to evaluate the performance of our model. We will load the accuracy metric, which is suitable for the MNLI dataset. This function, post-process MNLI prediction, is used to convert the textual generated answer of the model to actual indices. With all these ingredients, we are ready to instantiate a trainer class. First of all, we need to download from Hugging Face the starting point for our fine-tuning, which will be the GPT-J Eleuter AI checkpoint. It will take some time to download the weights. And once we have also the pre-trained model, we can create the trainer class. As you can see, it takes the training config, the evaluation config, the training dataset, the evaluation dataset, the pre-trained model, the tokenizer, the accuracy metric, and the post-process function. And it will provide a very simple API for both the fine-tuning and validation. Okay, once we have the trainer, we can do training with a single line, trainer.train, but we will first set the training steps to be a very small number, like 2. Let me look for the config parameter. Okay, so instead of 400 steps, we will just do a couple. Once training is finished, the weights are saved in the checkpoint directory, and we can navigate in the repository. And you can see that in the checkpoint directory, a subdirectory for the given run is created. And here you will find all the training steps that you have saved. So if you have a checkpoint configuration to save a checkpoint periodically, you will have more repository here. In our case, we just have 2 steps, and the only weights that are saved are the latest one. After training, we can do validation. Usually you would run this cell to validate the latest weights. But in this case, it won't have a lot of sense because we just run a couple of training steps. So instead, we are going to validate the pre-trained checkpoint, which we made available on Hugging Face. This checkpoint is the result of this fine-tuning. We are going to run this cell instead. You can find this checkpoint on Hugging Face, and this is the Hugging Face checkpoint. If you just run this cell, you won't have this initial phase where the weights are downloaded. And if you don't specify anything else, you will be running validation on the latest weights. If you instead want to validate a specific checkpoint, a specific path, you can set the evalconfig.checkpoint.load to the path of a given checkpoint. Once you have finished validation and you're sure that your weights are good, you can convert your checkpoint to a Hugging Face checkpoint. The trainer API provides a function, save Hugging Face checkpoint, to do this conversion automatically. Basically, what it does is it takes weights in this format and convert them to be compatible with the Hugging Face PyTorch model, so that you can later load them in the Hugging Face model and run them on any hardware, and you can upload the weights to the app. So what I wanted to show you is that in the terminal, you can navigate back from the run, and you will have the Hugging Face checkpoint folder where you have the Hugging Face weights. That's it. And this is exactly the format expected on Hugging Face. It's all for today. I hope the walkthrough was useful. And if you want more information, follow the links in the video to read our blog post. And if you want more insights into how GPT-J is actually executed on the IPUs, you can read the README in our example repository on GitHub. And moreover, if you have any question, you can join the Graphcore Slack community channel.